right, so it says, we had started last time talking about sums. So just as a matter of refresher, let's write our formulas over here. For sums, we have n over 2, first plus last. We have a sub 1 minus a sub 1 r to the nth over 1 minus r. And we have a sub 1 over 1 minus r. Now, in order to do oh wait, have we had this formula yet? I can't remember. Doesn't matter, it's up there now, we'll go with it. So let's look at number 4. Let's look at the sequence. And it says we are going to add up the first 90 terms. Okay. I haven't already done this problem, right? This is a brand new problem for you? Okay. So we're going to add up the first 90 terms. Now, anytime we're adding, we're going to use one of these formulas over here. What kind of a sequence is this? That's what you have to decide first. What kind of a sequence do we have? Arithmetic. And if it's arithmetic, we have one choice right here is our arithmetic formula. So it tells me I'm going to add up 90 terms, so that's going to be 90 over 2. The first term is negative 2. Remember, that means first term. Oh, brother. What does this mean? In this problem, what is that? Yeah, that's a problem because I don't know the 90th term. So I'm going to have to, over to the side, a separate problem, I'm going to have to figure out the 90th term. And that means I'll use my arithmetic term formula, which is this one. S is sum, A is term. So the 90th term, according to that formula, is the first term plus the common difference. And what's my common difference?
3.
Thank you. Times 89, which is 90 minus 1. A sub 90, A sub n. N is 90. So I'll figure out what that is. Negative 2 plus 3 times 89. That's 265. So that's what's going to go right here. That is not the answer to the question. That is the 90th term of the sequence, which is something I need in order to answer the question. So now I'm ready to go. So now I'll just take 45 times 263, and 11,835 is the answer to the question. I think we talked about this last time, that it is not uncommon for you not to have everything you need when you start a problem. So often you'll have to leave what you're doing, come over to the side, figure something else out, and then plug that in order to start or finish the problem. All right, anybody have a question about that? All right, the next one says I'm going to find the sum of 12 terms of this sequence. So always, 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 the first thing you have to do is figure out what kind of sequence you have so that you know what formula to use. We're finding S sub 12, that's what the problem tells me. What kind of sequence is that? Yoo-hoo! How are we getting from term to term? It's geometric, and the ratio is what? What am I multiplying by? 2.
2.
Yep. So my formula, it's geometric. This is my geometric formula right here. That's my geometric formula. It says find the sum of 12. It will be 0.1 minus 0.1 times 2 to the 12th, s sub n, s sub 12, n is 12, over 1 minus 2. Now, when we talked about this formula the other day, I suggested that before you type it in, you just figure out what your denominator is. So your denominator is -1. And then we're just going to type in 0.1 minus 0.1 times 2 to the 12th equals divided by -1. And I got 409.5. Anybody not get 409.5? All right, there's one more here. Here we go. We are going to add up 53 terms of this sequence. So I need to know what formula to use. So what's going on here?
Adding 5.
So the common difference is 5. It's arithmetic. So I'm using my top formula up there. That formula says n over 2 times first plus, shoot. That's the 53rd term, right? I need the last term in the list, the one out here. And once again, I don't have it. So now 2 days in a row, what do we do when we don't have what we need?
You go back to the other formula.
You go back to the other formula. And when you go back to the other formula, make sure you're going back to the appropriate formula. This is arithmetic, so I'm going back to my arithmetic formula. If I had a problem in a geometric sum, I would go back to this formula because this is my geometric formula. But I'm arithmetic, so I'm using this one. A sub 53 will be the first term plus the common difference times 52. A sub n, A sub n, n is 53. So n minus 1 is 52. So -18 plus 5 times 52. I got 242. Do not get excited. That is not the answer to the question. That is the 53rd term. So I'll plug that in. And for an answer, I got 5936. Anybody match that? For a final answer? Okay, good. I see some nods. That's super. Okay. Now we are going to find some sums of infinite series. Now here's the deal, kids. Neither one of these formulas, these two up here at the top, would work if the sequence is infinite. Because what does n stand for? We have all these n's in here. What do these n's stand for? N stands for what?
The term we're going to.
Exactly. And if the sequence is infinite, would there be a term that you are going to? No. Infinity means it goes on forever. So let me look at this sequence right here. What's happening in this sequence?
Dividing by 2.
Okay, which
Or
is this?
multiplying by 1.
Exactly. That's the way we'll think about it. The ratio is 1/2. But of course, multiplying by 1/2 and dividing by 2 are exactly the same thing. It's just in the formulas, we need a multiplier. So we got to think of it as timesing by 1/2. Now, we keep multiplying by 1/2. So these terms are getting smaller and smaller. Would you agree? Because they're getting smaller and smaller, their sum will have a limit. You will be able to add them up. Their sum will have a limit because the terms are getting smaller and smaller and smaller. If you are adding an infinite series, this is the formula you're going to use, an infinite geometric series. So, it's real easy. The first term is 3 and the ratio is 1/2. So that's 3 over 1/2, which is 3 times 2, or 6. So the sum of these terms, if you kept going forever and ever and ever, their limit is 6. The sum, not the limit of the terms, but the limit of the sum. If you added all these up, the sum would be 6. Now, the only way you can do that, kids, this is the only formula that sums infinite. So the fact that it has an R in it means the sequence must be geometric, and the terms must be getting smaller. If they're getting bigger, you have no limit, no sum. So they have to be getting smaller. So we'll add the caveat here that whatever your ratio is, its absolute value must be less than 1. So yours worked out great because your ratio was 1/2. It's summable. We typed everything in. There's our answer. Done. All right, let's look at the next one. What's going on here? Well, it's got to be geometric if I'm going to do the problem. Is it geometric?
Yeah.
And what's the ratio? What am I multiplying by?
-1/2.
Yep, absolutely. So my formula says 4 over 1 minus -1/2. Remember, the denominator is 1 minus r. So that's going to become 4 over 3/2, which is 4 times 2/3. So my sum is 8/3. As long as your terms are getting smaller and smaller, as long as you're multiplying by a number less than 1, you are all good to find the sum. Any question about that? That's your easiest formula to use, I think. Okay. Next one, doing the same thing. Is the sequence geometric? That's the first thing you have to decide. If you're going to sum an infinite series, you have to know that it's geometric, because this is the only way you can do it. So it has to be geometric. Are we multiplying by the same thing? Pardon me? 2/3, yep. Something's wrong with that microphone's a little fuzzy. 2/3, yep, we're multiplying by 2/3. So here we go. First term, over 1 minus the ratio. So 6 over 1/3 is 6 times 3. So that sum is 18. Wow. That is so, so, so easy. All right, one more, and then we're going to do something else. All right, is this thing geometric? And if it is, what am I multiplying by? Now remember, if you're at all confused, what you're asking yourself is, 3 times something is 4.5. 4.5 times that same something has to be this, and this times that same something is this. So you can just find the ratio. That's why we call it a common ratio. What's 4.5 over 3? It's 1.5. What's 6.75 over 4.5? Oh, it's 1.5 also. So I think this is geometric. And the ratio is 1.5, or 1.5, or 3/2. So the sum will be first term over 1 minus the ratio. Does that bother anybody?
It's bigger than 0. Or wait, 1 I mean.
It's bigger than 1. The ratio is bigger than 1. Does this even make sense? What's going to happen when you calculate that? You can calculate that. You can get an answer. But what's going to happen?
It's going to be negative.
Yeah. Does that bother anybody that I'm adding up these terms and coming up with a negative answer? That doesn't even make sense. This is not summable. Kids, if this is going on all the way to infinity, aren't these terms just getting bigger and bigger and bigger? There's no way to add them up. They're just exploding. So the sequence is divergent, which means a sum is not possible. So there is no answer to that question. It is a geometric sequence, but it isn't summable because its ratio is bigger than 1. All right, does that make sense to everybody? If you missed it the first time, do you see it now? All right, so now we're going to use this formula for a specific little purpose. All right, so here we go. We're going to consider this repeating decimal. Now, everybody knows what a repeating decimal is. If we wrote this out, it would be 0.4444444, dot, 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 dot. So see that dot, dot, dot? That reminds me of the problems I just did, the infinite series. And believe it or not, this is an infinite geometric series, because if I break it apart, I'll have 0.4 plus 0.04 plus 0.004 plus 0.0004 and so on forever. Now look at that. Does that make sense to you that it's just another way of writing that repeating decimal? This is an infinite geometric series. How am I getting from term to term? What do I multiply this by to get this? Yep, so my ratio is 0.1. When there is one repeating decimal place, your ratio will always be 0.1. I have one repeating number, 4. So this ratio will always be 0.1 in that case. So the sum, if I want to add all these up, the sum will be the first term over 1 minus the ratio, which is 0.4 over 0.9. In math land, we prefer not to have decimals in our fractions. So I'll just multiply the top and the bottom by 10, and my fraction is 4/9. So the answer to the question, the reduced fraction, is 4/9. That's easy to check. If you take your calculator out and do 4 divided by 9, it will give you repeating 4s. Now, there are other ways to change repeating decimals into fractions. If we have time, I'll show you another way. But in keeping with our infinite geometric series idea, this is a way to do it, and it's real easy. It's really easy. Let's look at the next one now, because it's a little bit different in that it has 2 repeating decimal places. So that would be 0.63 plus 0.0063, 0.00063, and so on. Does that make sense to everyone? Now, I have 2 repeating decimal places. So in every term, I am actually multiplying by what? Not 0.1. Someone talk to me, please. What am I multiplying by?
0.2.
No. What's 0.63 times 0.2? That wouldn't give me that.
0.01.
0.01, sure. You're multiplying by 1/100th. You're moving the decimal point 2 places in each term. 2 places is 1/100th. 1 place is 1/10th. All right, so now I'm ready to find the sum. So my first term is 0.63. My ratio is 0.01. So I have 0.63 over 0.99, or 63/99. Now you are supposed to answer in lowest terms. So what can I divide 63/99 by? 3. So 3 will bring it down to 21/33. Does it go any farther than that?
7/11.
So one more 3 can come out. I could have done 9 out of the original, or 3 twice, but yep, 7/11 is the fraction for 0.63 repeating. Let's double check that. 7 divided by 11 on my calculator. Guess what it gives me? Repeating 6 3s. Now, the next one is a little bit on the tricky side. Because while we can still write it as a series, there's a term in there that doesn't fit the pattern. So there's a 0.1, but that doesn't repeat. So then I have a 0.04, and then an 004, and an 0004, and so on. So go ahead and split it up like this, but notice that this guy is not part of the series, the infinite series. Because while we're moving the decimal point 1 place for all of these, we did something else here. So we're going to disregard him for a moment, and we're going to add up this part. This is actually the infinite series part of the problem, the repeating 4s. The repeating part of the problem is your infinite series. Well, what's my ratio?
0.1.
Yep, 1 decimal place is repeating, so my ratio is 0.1. Okay? I don't know what's going on. There's lots of people walking around the halls. Students. All right, so now I'm going to find my sum. So my sum is the first term, which is 0.04. Remember, I'm only doing what's in the bracket. I'm only doing the repeating part of the problem, over 1 minus 0.1. So I have 0.04 over 0.9. Now to simplify that, I got to get rid of those decimals. So I'm going to move everything 2 places. So 2 places would be 4 over 90. Got to move it 2 places. You have to move the numerator and denominator the same number of places.
Good morning, Cathedral. This is Aubrey Thornsberry in Technology. We are running a test of the AP system, and I'm going to read the mission and vision of the school with you guys. Cathedral, a premier Catholic high school.
Okay, I'm going to yell real loud because she's talking and she's saying important stuff about the mission and vision. We have more important stuff to do here. I know this reduces, but don't reduce it because we're not done with it. We still need to add that to the point 1. Do you remember that we left out at the beginning? So I need to take this part, this sum that I got, and I'm going to add 1/10. To add fractions, you need a common denominator. So I'll multiply this by 9. So I have 4 90ths and 9 90ths. 13 90ths is my final answer. To check that,
because it's in the tens place.
no, it's 0.1. 0.1 is 1/10. I'm adding that decimal back. I've already done the brackets. I'm adding that first number back in now separately, and it's 0.1. Literally, that is 0.1, which is 1/10. Now I'm checking my answer, 13 divided by 90. Oh my gosh, it gives me exactly what I wanted. So the moral of that story is, sometimes there's an extra number thrown in, or 2, and I just hang on to those and add them in at the final, after I get my sequence done. So the sum of the sequence worked out to be 4 90ths. And then I added in 1/10. Got a common denominator, added my fractions, and there we go. Let's do the next one. It's exactly the same thing. And you probably, because this is a very familiar decimal, you probably already know what the answer is, but let's go through the process. So this is going to be 2 plus 0.3 plus 0.03 plus 0.003 and so on. So this time we have a 2, whole number 2, and then we have our repeating decimal, 0.3, 0.03, 0.003. This does not fit the pattern, so I'm going to ignore it temporarily, and I'm going to add up the part that does fit the pattern. The repeating part of the problem, I'm going to add up. What is my ratio? I have 1 repeating decimal place, so my ratio will be 0.1. So the sum of the bracket sum is first term over 1 minus the ratio, which is 0.3 over 0.9, which is 3/9. Now, usually I don't want to reduce at this point, but in this case it isn't going to matter. So I'll go ahead and reduce. And that is the repeating part of the problem. You probably have seen that enough, you knew that. The 0.333 is 1/3. Well, there you go, we just got it. But that 1/3 still needs to be added to 2. So 2 plus 1/3 is 7/3. So your fraction is 7/3. And if you took out your calculator and did 7 divided by 3, you should get the original problem always. Alrighty? One more. This one's got a couple of extra numbers in it. Remember, your formula will only work on the infinite part of the problem, the sequence. So we have 1.741 repeating. So that's 1.7 plus 0.041 plus 0.0041 and so on. Remember, when you add decimals, you line up the decimal points. So if you lined up all the decimal points that I have written up here so far, you'd have 1.74141. That's all I did so far. Okay, so these are the decimals that would add up to give you your repeating decimal up here. This first number is not part of the pattern, so I have to ignore it, and I'm going to add up this part. You have 2 repeating decimal places, so what's your ratio? Yep, 0.01. You're moving the decimal point 2 places each time to accommodate the repeating. So my sum will be 0.041 over 1 minus 0.01. First term, remember, I'm only doing the repeating part. So 0.041 over 0.99. Now, in order to get rid of the decimals, I'm going to have to move it 3 places. So I'm going to have 41 over 990. I have to move it 3 places to get rid of all of the decimals in that fraction. I don't know if that reduces or not. It doesn't look very optimistic, but it doesn't matter. Don't reduce it yet, because what do we still need to do? That is the bracket. Don't we still need to add in this guy right here? So we're going to add 17/10. This is 1.7 or 17/10. So I'll get a common denominator by multiplying this one by 99. So then I'll have 17 times 99 plus 41. I'll have 1724 over 990. So I had to get a common denominator by multiplying this one by 99 over 99. So I got 990 down there. So 17 times 99 plus 41, I think is 1724. Does that reduce? That's my final answer as soon as I reduce it. Does that divide by anything?
You can take a 2 out.
For sure, we can take a 2 out, absolutely. Start with what you know. So we take out a 2, we get 862 over 495. We no longer can take out a 2, so we know we're done with 2's. Does 3 go into that? Nope. 5 doesn't go into that. I think we're done. Yep, I think we are done with that. So that should be our answer. Let's double check. 862 divided by 495. Yep, it gives me the decimal that I wanted. Okay. All right, let's look at some word problems now. All right, let's see. Some of these I took right out of your book. So when Super Balls sprang upon the scene, kids across were amazed. Okay. All right, so let's look at this situation. I'm now doing This is number 7, the first word problem. Somebody has dropped one of these bouncing balls from a height of 2 meters. So here we go. We dropped it down 2 meters. And then it bounces back up. And according to the problem, how far does it bounce back up? And what's
how much
Yep.
was dropped?
exactly? So what's 90% of 2? What's 2 times 0.9?
1.8.
1.8. And then of course it comes back down 1.8, right? Because whatever it went up, it has to come down. Now, how far is it going to go up next time?
of 1.8.
Yep, so 1.8 times 0.9, 1.62, and so on. Aren't I just going to keep multiplying by 0.9? Isn't that what's going to happen? And that ball is just going to keep going, infinitely many times. So I am going to sum an infinite geometric series, which is what all I've done today for the last few minutes anyhow, and the ratio is 0.9 because that's how I'm getting from term to term. Now what makes this a little bit different than the other problems we did is there's actually 2 series here. There's the downs and there's the ups. And they are not the same. Does everybody see that the downs and the ups aren't the same? Because the downs start with 2. So here is my sequence of downs. Let's do those first. They start with 2, and the ratio is 0.9. So that's 2 over 0.1, which is 20. So the downs add up to 20. I'm finding the total distance the ball travels, and that means I have to look at ups and downs. Tell me about the ups. How would I figure out what the ups add up to? All the downs add up to 20. What do the ups add up to?
Would it be a 1.8 over 1 minus 0.9?
You absolutely can do that, or you can recognize that the downs and the ups are the same except for this. So if the downs are 20, don't the ups have to be 18? Which is exactly what you'd get if you did 1.8 over 1 minus 0.9. That will give you 18. If you have these bouncing ball problems, the ups and downs are always going to match except for the first term. Sometimes the ball is thrown, and if the ball is thrown, then the ups and downs match exactly. But in this case, it was dropped, so the total distance would be 38 meters. 38 meters. The ups and the downs added together are 38 meters, 20 and 18. All right, let's look at the next problem. It says the first row of seating has 7 seats. There are 25 rows altogether, so come out here to the 25th term. Each row contains 2 more seats than the row preceding it. So if the first row has 7, then the second row would have 9, and then 11, and 13, and so on. Is that how you understand the problem? So we want to know how many seats altogether. So don't I want to sum these, you guys? Don't I want to find the sum of those 25 rows? Arithmetic or geometric?
Arithmetic.
So the sum of arithmetic is n over 2, first plus last. So here we go. We know we got 25 of them, and we know the first one's 7, but oh shoot, we're right back where we were earlier today. What's the matter? What do I not know?
Last term.
I don't know, but I don't know how many seats there are in the 25th row. So what I will do is pull up my other formula for arithmetic sequences, and I'll figure out what the 25th term is. It'll be the first term plus the common difference times 24. Oh, is that 55? Now, 55 isn't the answer, but that's what I'm going to put right over here. That is how many seats are in the 25th row. If I kept going out this way till I got to the 25th number, it would be 55. So now I can figure out how many seats there are altogether. Looks like there's 775 seats in section J of this auditorium. All right. Letter C, here we go. Tell me your thoughts. Pretend you're on your own and you need to come up with a strategy to do this problem. Letter C, patio construction.
You would start by putting 15 and 30 down in the sequence.
So we know that we got some kind of sequence. We go from 15 to 30. And we know there are how many numbers in this sequence?
16.
Yep. And we want to add those up, don't we? And we know it's arithmetic because they tell us. Oh my gosh, you guys, this is like the world's best problem ever. It's arithmetic. We know how many terms we have. We know the first one and we know the last one. That's it. That's going to be your answer. It might be a word problem and that might freak you out, but it shouldn't. That is the easiest problem in the world because they give you every piece of information that you need. All right, let's go. Let's get some more done here. And this is the lunch period, I know. But we're good. Let's get a few more done. Trey's decided he's going to begin saving. He sets aside 40, 46, 52, da-da-da-da. How much will he set aside on the 37th day? All right, so here's the question you ask yourself. Arithmetic or geometric?
Arithmetic.
Okay. Then you say to yourself, okay, do I want A sub n or do I want S sub n? In other words, do I want a term or do I want a sum?
Sum.
Not in question A. How much will he set aside on the 37th day? This is the first day, this is the second day, this is the third day. I want to know how much on the 37th day. So that'll be A sub 37. First term plus common difference times 36. That's how much money he's going to put in the bank, in his piggy bank, on the 37th day. It's just a number in that list. So 40 plus 6 times 36. $2.56. Please don't say 256 cents, because nobody says that. It's $2.56 is how much he would deposit in his bank on the 37th day. First day, second day, third day, 37th day. Now, see what's different about question B? How much will he have set aside if he does this for 100 days? So if he does this for 100 days, how much will be in the bank? Isn't that S sub 100? Doesn't that mean I want to add? I don't see a bunch of faces. I don't know where you people are. I hope you're paying attention. I'm supposed to be able to see your face. Please don't make this harder than it already is. All right, I'm going to find out the sum of 100 terms. It's arithmetic, so I will use my arithmetic formula, which says 100 over 2 times the first plus the last. This would be the 100th term in the list, and I don't know what that is. I know the 37th, I do not know the 100th. So won't I just do this over again, but with 100? So 40 plus 6 times 99. I got 634. Now I am going to leave that 634 because I left this as 40. So that's cents, so this has got to be cents. In the end, I'll change it to dollars. So now I'll add my 40 back in and multiply by 50. Oh, wow. Looks like he will have saved $337 after 100 days of following this savings plan. Okay, we're going to do another one here. Anybody have a question about that one? All right, Grace decides that she too will start saving. Her plan is to save 4 cents on the first day, so she's got a different savings plan. She's going to save 4 cents and then 12 and then 36 and so on. How much will she save on the 37th day? What's different about Grace's situation?
It's geometric.
It's geometric. And since it's geometric, I'll have to use my geometric formula, which we haven't had on the board very much today. The geometric formula, remember, is a sub 1 r to the n minus 1. So the 37th term will be 4 times the ratio here is 3, we're timesing by 3, to the 36th. Oh, this is going to be huge. 4 times 3 to the 36th. Okay, now the number comes out to be 6.00 times 10 to the 17th, but that would be cents, right? So that's 6.00 times 10, oh, that was 17, times 10 to the 15th dollars. Good luck with that, Grace. How much will she have set aside after saving for 100 days? Oh my goodness. Oh my goodness. So Grace is going to do this for 100 days. How much will she have saved? Well, it's geometric, so we'll take our first term minus our first term times the ratio to the 100th. I hope my calculator will do this, actually. That's going to be a giant number. So 4 minus 4 times 3 to the 100th over negative 2. All right, let's see what happens. Oh, it does it. Good. So 1.03 times 10 to the 48, that would be cents, since I started with cents. So 1.03 times 10 to the 46 dollars. Wow. Pretty amazing. Anybody have a question about those two problems we just did? Trey's saving plan and Grace's saving plan.
Why do you subtract 2 from the exponent on the 10?
When you go from cents to dollars, you move the decimal point 2 places. There's 100 cents and a dollar, so I'm like dividing by 100. If I had 204 cents, that's $2.04, or $2.04. I move the decimal point 2 places, which changes the exponent.
Okay, thank you.
All right, let's do one more. Still have time. I know, quit rolling your eyes. Stop it. We gotta get through the math. We have to spend our time wisely. Here we go. A ball, we just did this. A ball is dropped from a height of 30 feet, bounces back up 7/10 each time. So if it bounces back up 7/10, it must go up 21 and down 21. And then up, I don't know, whatever 21 times 0.7 is. That's how you're figuring out how far up it goes. You just keep multiplying by 0.7. Okay, it's going to just keep going. How far will it travel before coming to rest? So remember, the ball is moving down and up. So you need to sum all of the downs and get an answer, and then you need to sum all of the ups and get an answer. Now, I like to start with the first number I've been given, which is 30. So I'll do my downs. So 30 over 1 minus 0.7. There's nothing magical about that, guys. They tell me the first term is 30, and they tell me the ratio is 0.7. I keep multiplying by 7/10. So that's 30 over 0.3. What's 30 divided by 0.3?
So 900.
I thought it was 100.
It is.
Yeah, 100. So the downs are 100. Now remember that the ups match the down. For every up, there's a down exactly, except for this first one, right? So if the downs are 100, wouldn't the ups be 70? 100 minus the 30? So the total distance the ball has traveled is 100 or 170 feet. 170 feet will be the total distance it travels before it comes to rest. Okay, well, we have 3 problems to go, but we'll save those for tomorrow. And then we'll do a little review tomorrow for a quest on Thursday. Okay, don't forget cereal on Wednesday morning before school. Anybody have any questions? All right, have a great day. See you later.
Thank you.
Thank you.
Bye-bye. Wake up, George.